Have you ever noticed that copper, the metal in pennies and electrical wires, isn't silvery like most metals, but instead has a distinctive red-orange hue? In a world where iron is gray and aluminum is silver, copper stands out with its warm color. This isn't a trivial detail. That reddish color is a clue to copper's unique chemistry and electron structure. Copper is a soft, highly conductive metal, one of the best conductors of heat and electricity, and a freshly exposed surface of pure copper indeed shows a pinkish-orange color. In this video we will explore why copper is red and discover several of its fascinating chemical properties through 3 experiments. Along the way, we will see how those properties connect to real-world applications, from historical uses like early fabric production to modern technology and even medicine. By the end, not only we will answer the question of copper's color, but we will also appreciate how this element's chemistry has made it so important in our lives. And this will even extend to my personal life, as I will find out through one of those experiments that I probably have diabetes. Welcome to Cube Chemistry, where we'll discuss all the elements of the periodic system and also do experiments. So if you like this video and want to see more, make sure to like, subscribe and hit the notification bell so you will never have to miss another episode. Also make sure to fill in the poll in the post section of the channel for next week, as we will be discussing another element. Now before we dive into the experiments, let's set the stage. Copper has been known to humans for thousands of years, and it's one of the few metals found in usable native form and was likely the first metal ever melted from ore. Its name comes from cuprum, Latin for cypress, where the Romans mined it. Entire ages of human history, the Copper Age and the Bronze Age, are named for it. Copper's durability, conductivity mean it's everywhere around us today, in electrical wiring, plumbing, coins, and even in the cells of our bodies. But copper's color, that reddish tint, is an immediate visual giveaway that something is special about its electrons. Let's investigate what makes copper behave the way it does through some experiments that highlight the key properties: complex ion formation, oxidation-reduction reactions, and metallic crystal growth. Now, of course you want to see these experiments, but in our video about copper we forgot to answer the world's most important question about copper: can you lick it? Now technically yes, you can lick copper. Also the periodic licking table is pretty optimistic about it, but it's not recommended, of course. A common example is the so-called penny test, where people put a penny in their mouth or rub it against their skin. Older pennies, pre-1982 in the US, are mostly copper, while newer ones are copper-plated zinc. Now when copper touches saliva, it can create a metallic bitter taste due to tiny chemical reactions that release copper ions. In small, brief contact, like licking a clean copper penny, it's unlikely to be harmful, but copper isn't food safe in large or repeated doses. In fact, too much copper can irritate your stomach or cause metal toxicity. And if a penny is dirty or corroded, you're introducing bacteria or toxic compounds like verdigris, green copper salts, which definitely aren't safe to ingest. So while licking copper probably won't hurt you once, it's best left out of your science experiments or your mouth. Now no worries if you're not a chemist. I am not a chemist either, but we'll keep things simple and fun, focusing on the big ideas and why they matter. Now our first stop on the copper tour is a splash of color. We start with a solution of copper 2 sulfate, a salt that dissolves to give copper 2 ions in water. Copper sulfate solution has a mild blue color, as you can see here. If you've seen the blue crystals sold as root killer or the blue liquid in chemistry class, that's the one. Now we slowly add a few drops of ammonia solution, and what do you think happens? Immediately a pale blue precipitate forms, turning the solution cloudy. This is copper 2 hydroxide, a solid that appears because ammonia, which is a weak base in water, pulled some hydrogen off the water molecules to make hydroxide. Now those hydroxide ions grab onto the copper ions and create insoluble copper hydroxide, hence the light blue solid forming. Now, as we keep watching and we add more ammonia, a dramatic change occurs. The bluish solid begins to dissolve, and the liquid in the tube turns into a deep royal blue color, far more intense than the original copper sulfate solution. It's a beautiful transformation. We've gone from sky blue to an almost ink blue solution. Chemically, what is happening is that the excess of ammonia starts bonding directly to the copper ions, displacing the water molecules that were attached to those copper ions. The copper ion in solution normally sits around by water molecules, a hexaqua complex. But ammonia is a better ligand partner for copper. So copper exchanges some of those water partners for ammonia partners. The result is a complex ion called tetraamine copper 2 with this formula. This new complex has a different shape and electronic structure, and that's why the color is so much deeper blue. In essence, the copper ions, electrons, interact with the ammonia differently than with water, absorbing and reflecting light in a new way, hence the striking color change. Now, this deep blue complex has a name, Schweizer's reagent, named after Swiss chemist Matthias Eduard Schweitzer. In 1857, Schweitzer discovered an interesting ability of that solution. It can dissolve celluloses, which is the fibrous material in cotton and wood pulp. Now, cellulose doesn't dissolve in water or most ordinary solvents. That's why cotton clothes stays intact in the wash. But somehow this copper ammonia solution was able to chew it up. Chemists quickly put that to use in the late 19th century by dissolving cotton in Schweizer's reagent and then squirting that solution into acid. They could reform the celluloses into fibers. Now, this was the birth of rayon, the first artificial silk, and a similar process was used to make transparent film called cellophane. So, the very blue solution we made in our little test tube was once part of an industrial revolution in textiles. It's a great example of how a curious chemical property, copper, forming a stable, deeply colored complex with ammonia, found a real-life application in manufacturing. Now, beyond rayon, the formation of copper's ammonia complex demonstrates a more general property of copper and other transition metals. They form coordination complexes, and many of these are vividly colored. Now, in fact, copper compounds have long been used as pigments. Some of the most famous blue and green pigments owe their use to copper. For example, the blue of azurite and the green of malachite are due to copper 2 salts. Artists in the past ground those minerals to make paint. Even the copper complex we made in a more concentrated form have been used to identify fibers, as in the Schweizer's test for wool versus cotton, and to analyze cellulose in labs. To summarize this experiment, adding ammonia to copper sulfate showcases copper's property of forming complex ions, foreshadowing the bigger question, why copper itself is red. We'll get closer to that answer as we continue exploring copper's chemistry. Our next experiment takes us into the realm of chemical tests and another interesting ability of copper, to toggle between different oxidation states. In simple terms, to undergo redox reactions. We'll use a classic test from organic chemistry known as the Fehling's test. Now, a few weeks ago, we also discussed oxidation states of manganese and how that resulted in color changes. If you want to see that video, click on the link in the description. Now, let's go back to the test. Developed by German chemist Hermann von Fehling in 1849, it was historically used to detect sugars, especially to check for glucose in urine, as an early diagnostic for diabetes. It's basically a solution of copper 2 in a special alkaline mixture that will react with certain types of molecules, reducing sugars, and give a color change. Now, what is in this Fehling solution? Traditionally, it comes in 2 parts that are mixed before use. Fehling's A is a solution of copper 2 sulfate, which is blue, and we saw earlier. And Fehling's B is a solution of sodium hydroxide, a base with tartrate, a compound from tartaric acid. Now, when combined, the copper 2 ions form a complex with the tartrate in the basic solution. This complex keeps the copper in the solution and gives a clear deep blue color. In our simplified experiment, we can simulate Fehling's solution by mixing copper sulfate with a base like sodium hydroxide to get a similar blue suspension of copper hydroxide complex. So now let's get to the interesting part. We add a sample that contains glucose, for example a bit of glucose sugar, in the solution, and then gently heat the mixture. If glucose is present, an oxidation-reduction reaction occurs. After a bit of heating, you will see the solution's color change from blue to greenish to yellow, and then an orange or brick red solid starts forming in the test tube. By the end, we get a reddish-orange precipitate, and the liquid above is a much paler color. Now, this positive result indicates glucose, a reducing sugar, is indeed in the sample. Chemically, what happened is that copper-2, the blue copper ions in Fehling's solution, got reduced to copper oxide, which is an orange-red solid. Glucose, meanwhile, was oxidized. Essentially, it got partially burned, in chemical terms, into a form of acid. The important point is that copper went from an oxidation state of +2 to +1, trading its electrons with glucose. We forced copper to change who it partnered with and how many electrons it has. Quite different from the last experiment where copper stayed in the +2 state and just swapped companions, water for ammonia. Here, copper's oxidation state actually changed, demonstrating its flexibility in redox chemistry. Now, Fehling's test is a great example of copper acting as an oxidizing agent. It accepts electrons from another substance, glucose in this case, and gets reduced. The tartrate in Fehling's solution is actually there to keep the copper available in solution and prevent it from just precipitating as copper hydroxide immediately. Now, once glucose is added and we heat it, the complex breaks down as the reaction proceeds, and insoluble copper oxide forms, giving that brick red deposit at the bottom of the test tube. If no reducing sugar is present, nothing happens and the solution would remain blue. So the appearance of the red precipitate is a clear positive indicator. On the left, in the image below, is Fehling solutions with no glucose, still blue, and on the right is a tube after a positive test with the reddish-orange copper oxide that formed. Historically, the reaction was very significant. Doctors in the 19th century used Fehling solution and later the similar Benedict solution to test patients' urine for sugar as a diagnosis for diabetes. They would literally mix the chemicals and boil the test tube. If turned red, that indicated excess of glucose. Now, while that sounds simple, it was a bit tedious and required careful technique. Nowadays, of course, we use enzymatic test strips or electronic glucometers for a quick blood sugar reading. But those early copper solutions were the prototype for today's glucose test, a big step in chemical diagnostics. Okay, time for a mildly questionable decision in the name of chemistry. I'm testing my own urine using our simplified version of the Fehling's test. Historically, this was used to detect glucose, especially as an early check for diabetes. So, if my pee has any glucose in it, the lovely blue copper solution should turn orange-red when heated. If it stays blue, that's a good sign for my pancreas. For contrast, and just to make sure the chemistry works, I've also spiked a second sample with glucose. So, here is the result. It seems like I indeed have sugar in my urine. After this, I did go to a doctor to do some state-of-the-art testing, and we found out that indeed I've got an elevated blood sugar that seems to be indicating diabetes, probably type 2. Now, I must say that the doctor's assistants were pretty impressed by the fact that a test from the 19th century was accurate enough and got me to go to the doctor. Now, this is part chemistry, part curiosity, and 100% commitment to the bit. Please note, this is not a medical test, and no, you probably shouldn't do this at home. So, here we have the result of my tests. Fehling solution was also used in food analysis, for example, to measure how much sugar was produced when starch breaks down, using the amount of red precipitate to gauge sugar levels. So, what property of copper does this experiment highlight? Well, it's the ability of copper to cycle between oxidation states and precipitate in electron transfer reactions. In Fehling's test, copper-2 is reduced to copper-1, the copper oxide, by the sugar. Copper is pretty special in that its +1 and +2 oxidation states are both stable enough to exist in a reaction like this. Many other metals either don't have multiple common states or they aren't as easy to interconvert. Copper's position in the periodic table with an electron configuration that can stabilize both +1 and +2 states makes this possible. This flexibility is not just useful in test tubes, it's also exploited in many real-world contexts. Now, for instance, copper compounds are used as catalysts in some oxidation reactions in industry, and copper 2-sulfate has been used as a fungicide and algicide in agriculture for long term, partly because it can switch oxidation states to generate reactive oxygen that kills microorganisms. The principle is similar. Copper's redox activity can disrupt the metabolism of fungi and algae. Even in our bodies, copper's ability to go between +1 and +2 is crucial. Enzymes like cytochrome C oxidase in our mitochondria use a copper center cycling between oxidation states to help us respire. We will touch more on copper's biological side later, but keep in mind the little color change with glucose echoes a big theme of copper chemistry. It readily gives and takes electrons. In summary, experiment 2 showed us a redox reaction of copper. We observed a clear visual cue, blue to red, that copper was changing form, and we connected it to a historical test, the Fehling test. Copper's capacity to undergo such reactions underlies its role in analytical chemistry and in various applications like antifungal agents, and it even lays groundwork for understanding copper's electrical properties and corrosion behavior, which we'll explore next. After making blue solutions and red precipitates, it's time for something more solid. Let's grow some copper metal crystals. This experiment demonstrates copper's metallic nature and how it can be deposited from a solution, highlighting principles of electrochemistry and corrosion. One way to do this is often called the copper tree or the copper cementation experiment. The setup is simple. Take a solution of copper 2-sulfate in a container and introduce a piece of more reactive metal such as iron. For dramatic effect, we can create layers. We put some solid copper sulfate at the bottom of a jar, and we covered it with a layer of table salt, sodium chloride. We added some water to dissolve and form a stratified solution. And then we placed iron on top, like iron powder. And then we leave it alone for a while. Several hours, and in our case, several days. What happens is almost magical to watch. Spindly branching copper metal crystals begin to form and grow downward from the iron layer, often making tree-like or coral shapes with a shiny reddish color. We are literally growing solid copper out of the solution. So what's the science behind this copper crystal garden? It's a type of single displacement reaction, which is also an electrochemical reaction. Iron is higher in the activity series than copper, meaning iron atoms are more eager to give up electrons than copper atoms are. When iron comes into contact with the copper sulfate solution, an exchange occurs. The iron metal dissolves and oxidizes to iron 2+ ions, and simultaneously the copper ions in the solution gain electrons and get reduced to copper metal, which plates out. The overall reaction is this. Usually, if you just drop an iron nail into a copper sulfate solution, you'll see the nail gradually get coated with a layer of copper. And this is also what we did in a previous solution. The blue solution will fade into pale green as iron 2+ forms. In our experiment, we added a twist with the salt layer. The sodium chloride helps moderate the reaction. It sets up a barrier and creates a gradient that slows the diffusion of copper ions towards the iron. Now, because the reaction is slowed and spatially separated by the salt layer, copper doesn't just immediately plate onto the iron surface in a uniform way. Instead, the copper ions migrate slowly and deposit more delicately, building up dendritic crystals that can extend into beautiful shape. The salt also introduces chloride ions, which can form intermediate copper complexes and affect crystal growth. You might notice a greenish layer initially, likely a copper chloride species, but eventually pure copper forms as a reddish layer. The end result after a few days is a copper tree with metallic copper leaves and branches growing in the jar. Or at least that's what it should be. In our case, what we can see is no leaves, not really red anything, it's more yellow, and it looks like a moldy food mess rather than beautiful crystals. Now what's really interesting is that this setup should create a tiny electrochemical cell spontaneously. The iron serves as an anode, it loses electrons and corrodes, and the copper ions accept those electrons as the cathode, where copper metal deposits. In fact, the copper that initially plates onto the iron can itself become a conductive path, and further copper can deposit on top of that, extending outward as long as iron continues to supply electrons. We've basically made a rudimentary battery or galvanic cell. Iron is being consumed, like the negative terminal, and copper is being produced on the positive side. Now this closely relates to how corrosion works when two different metals are in contact. If you connect iron and copper in moist conditions, the iron tends to corrode, rust, faster because it will preferentially oxidize, protecting the copper, exactly what we see in our experiment. Now, engineers have to be careful about this phenomenon, known as galvanic corrosion. When designing plumbing or structures, if you connect copper pipes and iron pipes without proper insulation, the iron might corrode at the junction due to this effect. On the flip side, humans have harnessed this type of process beneficially in electrochemistry. One big use is in electroplating and electro-refining. For instance, to purify copper industrially, impure copper metal is made the anode in a copper sulfate solution, and a pure copper sheet is the cathode. When a current is applied, copper dissolves from the impure anode and plates onto the cathode as pure copper. Over time, you accumulate thick sheets of 99.99% pure copper, exactly the process used to get high purity copper for electrical wires. In our experiment, the iron was essentially acting like the anode, providing electrons, and the copper ions were plating themselves without us even needing a battery. The chemical reactivity difference drove the current. We could also do something similar by using a battery. For example, using electricity to plate copper onto a metal object in copper sulfate bath, which is how shiny decorative copper plating or circuit board copper layers are made. In any case, the formation of those copper crystals demonstrate how copper can conduct electrons and be deposited in a controlled way. In fact, with careful control of current, one can grow a very large pure copper crystal by electrolysis. Some hobbyists and chemists do this over weeks to get mesmerizing crystal specimens. Let's not forget real-world applications. Copper plating is widely used across industries. For example, in electronics, a thin layer of copper is plated onto circuit boards and connectors to make them highly conductive. Copper plating on steel components can improve corrosion resistance and is used in automotive parts like on brake line fittings to protect against salt corrosion. Copper's antimicrobial property, it naturally kills many microbes on contact, has led to copper coatings on hospital doorknobs and metallic instruments to reduce the spread of germs. And historically, the bottoms of wooden ships were plated with copper sheeting, not to prevent the iron nails from rusting away, but also because copper repels barnacles and algae, a phenomenon called anti-fouling. Now that's why old sailing ships and even modern boats often have a copper-based paint or plating on their hulls. Marine organisms don't like attaching to copper. The copper will slowly oxidize to a protective patina, but won't degrade like iron would. Speaking of patina, if you've ever seen a green copper roof or the Statue of Liberty's green surface, that's another aspect of copper's corrosion behavior. When exposed to weather, copper slowly forms verdigris, a green layer of copper carbonate and sulfate that actually seals off the metal underneath from further corrosion. Unlike rust on iron, which flakes off and exposes new metal, copper's patina sticks tightly and protects. This is why copper roofing can last for centuries. The Romans' Pantheon bronze, mostly copper roof, for instance, is still around after nearly 2,000 years. Our experiment with copper crystals thus ties into the broader idea that copper is relatively corrosion resistant. It prefers to deposit as a noble metal in our jar, and once solid, it doesn't rapidly deteriorate further. Now, to recap experiment 3, we witnessed copper metal deposition in the form of crystalline growth. It highlighted copper's excellent conductivity and how it precipitates in electrochemical reactions. We saw that a more reactive metal, iron, will sacrifice itself to allow copper ions to turn into copper metal, demonstrating copper's noble character. It's less easily oxidized. This experiment is like a miniature model of both geological processes, how copper can form in nature. Indeed, similar redox reactions over long times can lead to pure copper nuggets in rock veins, and industrial processes, electroplating and refining. So after exploring 3 very different experiments, let's step back and tie everything together and answer the big question, why is copper red? What is it about copper that explains the colorful chemistry we saw and its usefulness in so many areas? The answer lies in copper's atomic structure and position on the periodic table, which give it a set of remarkable properties. Copper has the atomic number 29 and its electrons fill up orbitals in a unique way. It ends up with a filled 3d shell and 1 electron in the 4s orbital. This may sound technical, but the key point is that all those electrons are what make transition metals like copper able to form colored compounds. In the first experiment, the ammonia experiment, the d electrons of copper-2 were rearranging in the complex and absorbing certain wavelengths of light, producing blue. In the solid metal copper, the situation is a bit different, but related. The metal's electrons can absorb light in the visible range. Most metals, like silver, aluminum, iron, appear silvery because they reflect almost all visible light uniformly. Their electrons require energy in the ultraviolet range to get excited, so visible light just bounces off. Copper and gold are exceptions. They have electrons that can absorb some visible light. In copper's case, its electrons absorb frequencies at the blue end of the spectrum. That means the light reflected from copper is lacking in blue and violet. It's enriched in the red and orange frequencies that weren't absorbed, so we perceive copper as that reddish-orange color. Gold similarly absorbs blue-green and appears yellowish. This phenomenon is partly due to something called relativistic effects and the detailed quantum behavior of those d and s electrons. But in a nutshell, copper is red because its electron configuration causes it to interact with light differently than colorless metal. It's literally a case of quantum physics at play in the shine of a penny. Thus, the question, why is it red, leads us to discuss electron transitions. And we saw examples of electron transitions causing color in copper solutions chemistry as well. Copper commonly exists in 2 oxidation states in chemistry, +1 and +2. We saw the +1 in the form of copper 2 oxide in Fehling's test, and +2 in all our solutions. It can even exhibit in +3 or others in some complex scenarios, but +1 and +2 are by far the most prevalent. Now, why is this important? Because it means copper can gain or lose an electron relatively easily, making it versatile in redox reactions. In our experiments, copper +2 was able to gain an electron and become copper +1 in experiment 2, and gain 2 electrons to become copper 0 metal, experiment 3. Yet copper metal doesn't give up its electrons willy-nilly in everyday conditions. It's stable enough that we can have copper roofs and coins that don't spontaneously corrode to nothing. So copper sits at a kind of a sweet spot. It's not as reactive as, say, iron or zinc, which corrode or oxide quickly, but it's reactive enough to participate in chemistry when conditions are right, like in a battery or with the right reagents. Now, this is one reason why copper is ideal for electrical use. It doesn't form an insulating oxide easily. It mostly stays metallic unless provoked, and even when it oxidizes, it forms that protective patina rather than flaking rust. Copper's d-electron configuration also means it loves forming coordination complexes, as we saw with the ammonia and with tartrates. In biological systems, copper is often found at the active sites of enzymes bound to nitrogen or oxygen ligands, kind of like how it bound ammonia in our experiment. These complexes allow copper to hold onto other molecules and facilitate chemical reactions, like electron transfer in enzymes. The vibrant blue of the copper-ammonia complex is one instance of coordination chemistry. Another everyday example is the blue color of the gemstones turquoise and the greens of malachite, all due to complex copper minerals. The fact that copper compounds have color made them easy to spot and use by ancient people for paints and dyes. And chemists continue to use those color changes as signals in analytical tests, like we did in the Fehling solutions or the ammonia test. I really have to call the doctor. Copper's single 4s electron also contributes to the sea of electrons in metal copper that makes it an excellent conductor. Copper metal allows electrons to flow through it with very little resistance. It has one of the highest electrical conductivities of any metal. Only silver and a couple of others are better, and silver tarnishes easily, so copper is the go-to. This conductivity is directly tied to why we saw copper plating happening in experiment 3. The electrons from iron moved so freely into the copper deposits. Those free electrons are also what reflect light and give copper its metallic luster, in addition to the color tint discussed earlier. So copper's red color and its conductivity are two sides of the coin of its electronic structure. It has an electron structure that's uniquely suited to both absorb certain light and to move charge efficiently. Copper is often described as noble metal, not as noble as gold or platinum, but noble in the sense that it doesn't oxidize easily in plain water or air. Yet it's just reactive enough to engage in the rich chemistry we've demonstrated. This balance is part of what makes copper so technologically and biologically significant. Its compounds can kill microbes, hence copper sulfate in agriculture and copper surfaces in hospitals. But metallic copper can safely carry drinking water in pipes without poisoning us. In fact, it also helps inhibit bacterial growth in the water. Copper's role in history from the Stone Age onward is no accident. Its properties made it accessible. It melts at a moderate temperature, alloys to form harder bronze, it resists corrosion, and useful, it conducts heat and electricity. It's easy to shape, and yes, it's pretty to look at. Even the red color was likely a visual attraction for ancient metalworkers. It looked like a shiny reddish-orange stone when first extracted, something novel compared to dull rock. So why copper? Because it sits at the crossroads of art, science, utility, and beauty. The experiments we performed highlighted that copper can form beautiful colors, undergo important chemical reactions, and yield useful solid metal. These are all direct outcomes of copper's atomic personality. Few other elements could have given us blue vitriol, copper sulfate, to dye fabrics, bronze swords for conquerors, wiring for the information age, green patina for iconic statues, and blue solutions to detect sugar in a lab. Copper did all that and kept its title as the only red metal in common use. Now that's a colorful character. We began with a simple question: why is copper red? Copper's red color is a hint at an unusual electron configuration that leads to selective light absorption. By exploring 3 experiments, we uncovered different facets of copper's behavior. In the copper sulfate plus ammonia experiment, copper showed off its ability to form complexes and displayed a dramatic color change, blue to deep blue, without even changing oxidation state. This demonstrated copper's affinity for certain ligands and produced a reagent so useful it helped launch the synthetic fiber industry. In the Fehling solution test, copper's role as an oxidizing agent came to light, flipping from copper plus 2 to copper plus and giving the telltale color change from blue to yellow. We saw how this property was applied in early medicine to test sugar in urine. And this is why I now have to call a doctor. Literally a life-saving application at the time. And it underscored copper's capacity to shuttle electrons, a property vital to both technology and biology. The test helped me on a personal level as well, as it detected the high blood sugar levels in my body and the fact that I need to go to a doctor to get that tested. In the copper crystal experiment, we watched copper metal emerged out of solution, emphasizing its conductivity and noble nature. This connected to how we refine copper for 99.99 pure metal in industry, and how copper protects itself and other metals from corrosion by plating out and forming stable layers. It was like watching a tiny version of copper mining and metallurgy happening before our eyes, as well as a demonstration of galvanic corrosion in action. Next time you hold a copper penny or plug in a copper wire, take a second to appreciate the subtle dance of electrons that give it that warm glow and all those remarkable properties. Copper isn't just a metal, it's a story. And one that's been unfolding for millennia, shining bright and yes, red all along. Now we would like to thank the members that support our channel. Thanks for doing that, we really appreciate that. Now if you think we missed anything, tell us in the comments, and if you want to know more about properties and color, watch this video about manganese next.